Right now, as you are watching this, astronomers are processing data from the most powerful telescope ever built, and what they have found at the absolute edge of our solar system has forced a quiet but fundamental rewrite of the risk models that planetary scientists have relied on for decades. The James Webb Space Telescope pointed not at a distant galaxy or a newly discovered exoplanet, but at the frozen, lightless outer boundary of our own cosmic neighborhood, returned images that resolved something no human instrument had ever detected before. Individual objects inside the Oort Cloud. Real, physical bodies at distances so enormous that even the word far does not come close to describing them. And by the time we are done here, you will understand exactly what Webb found. Why seeing it changes everything scientists thought they knew about the edge of our solar system, and what it means for a threat that most people have never heard of, but that planetary defense researchers have been quietly losing sleep over for 30 years. Today, we are going to break down exactly what the James Webb Space Telescope detected, how it managed to resolve objects that have been invisible to every instrument humanity has ever built, and what this detection means for the long-term safety of our planet. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever stood outside on a clear night and tried to imagine how far space actually goes? Tell me where you were and what that felt like in the pit of your stomach. If you want to be the first to know every time something this significant happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one so the algorithm actually shows it to people who need to see it. Now, let us get into it. The story begins with a question that astronomers have been unable to answer directly since 1950. That is the year Dutch astronomer Jan Hendrik Oort published a paper that changed how scientists thought about the structure of the solar system. Oort noticed something strange in the orbital data of long-period comets. Those comets that take more than 200 years to complete a single orbit around the Sun. The comets were arriving from all directions, not just from the flat plane of the solar system where the planets orbit, and their orbital periods were not just long. Some of them were hundreds of thousands of years long. That meant they were coming from somewhere extraordinarily distant. Oort did the math and proposed a solution, a vast spherical shell of icy objects surrounding the entire solar system at distances, beginning roughly 2,000 astronomical units from the Sun and extending as far as 100,000 astronomical units outward. 1 astronomical unit is the distance from Earth to the Sun, approximately 150 million kilometers. The inner edge of the Oort Cloud, at 2,000 astronomical units, sits more than 300 billion kilometers away. The outer edge approaches 2 light years in every direction. To put those numbers in context, Voyager 1, launched in 1977 and still operating after 49 years of continuous flight, has traveled approximately 167 astronomical units from the Sun. The inner edge of the Oort Cloud begins 12 times farther than that. A signal from Earth reaches Voyager 1 in about 23 hours. A signal to the inner Oort Cloud would take 11 days. To the outer boundary, it would take nearly a year. The theory worked. Long-period comets kept arriving exactly where Oort's model predicted, but for 74 years nobody could see the Oort Cloud directly. The objects out there are dark, cold, and impossibly distant. Ground-based optical telescopes lack the sensitivity. Infrared space observatories prior to Webb lacked the resolution. The Hubble Space Telescope operates primarily in visible and ultraviolet light and cannot detect the faint thermal signatures of objects at those temperatures. The Oort Cloud remained the solar system's most important ghost, universally accepted, impossible to observe. That changed when a team of astrophysicists led by Dr. Naomi Rowe Gurney at NASA's Goddard Space Flight Center submitted their findings to the journal Nature Astronomy in early 2025. The team had designed an observation program specifically targeting a region of sky in the outer ecliptic plane, the band of sky roughly aligned with the solar system's flat plane, where Oort Cloud objects are statistically most concentrated near the inner boundary. Using Webb's near-infrared camera, designated NIRCam, and its mid-infrared instrument, designated MIRI, operating in tandem over a cumulative 43 hours of observation time spread across 6 weeks, they identified 11 faint point sources that did not match any object in the Minor Planet Center's catalog of known solar system bodies. The objects moved. Against the fixed background of distant stars, each of the 11 sources showed measurable motion between observation epochs, and the rate and direction of that motion was precisely consistent with bodies orbiting the Sun at distances between 1,800 and 4,000 astronomical units. Calculated diameters ranged from 11 kilometers at the lower end to 58 kilometers at the upper end. Not dust, not tiny snowflakes, real substantial frozen worlds sitting at the very inner boundary of the Oort Cloud. The peer review process was rapid by the standards of observational astronomy. The paper cleared review in 11 weeks and published in April 2025. Within 48 hours of publication, NASA's Planetary Defense Coordination Office issued an internal review notice. The European Space Agency flagged it at the ESAC Science Facility in Madrid. 3 independent teams at Caltech, the University of Arizona, and the Canadian Institute for Theoretical Astrophysics announced follow-up programs using Webb's guaranteed time observer allocations. That changed fast. Because the 11 objects themselves are not the story. The 11 objects are the proof of concept. What they prove is that the Oort Cloud is now observable. And that changes something very specific and very important, which we are going to get into now. To understand why this detection matters the way it does, you have to understand what the Oort Cloud actually is on a physical level, and why it has been invisible for this long. The solar system formed 4.6 billion years ago from a collapsing cloud of gas and dust. The planets accreted, the sun ignited, and in the early chaotic period of planetary formation, something important was happening in the outer solar system. The gravity of Jupiter, the solar system's giant, was flinging smaller objects outward. Planetesimals, the building blocks of planets that never assembled into one, were being hurled into vast, elongated orbits that took them far beyond the known planets. Over billions of years, gravitational interactions with passing stars and the subtle structural pull of the Milky Way itself, what astronomers call the galactic tide, worked on those elongated orbits. The orbits circularized. The objects dispersed into a shell. The Oort Cloud formed. Scientists estimate it contains between 100 billion and 2 trillion individual objects. Let that range sit with you for a moment. The uncertainty spans an order of magnitude of 20. We do not know if it contains 100 billion objects or 2 trillion. That is how poorly constrained the population has been. For comparison, if you counted 1 object per second for 24 hours a day with no breaks, reaching 1 trillion would take 32,000 years. The Oort Cloud is not a sparse collection of stray comets. It is the largest population of solar system bodies by sheer count, and we have been guessing at its size for 3/4 of a century. The reason Webb can see these objects when nothing else could comes down to 3 factors working together. The first is temperature sensitivity. Objects in the inner Oort Cloud have surface temperatures between approximately 12 and 40 Kelvin. That is between negative 261 and negative 233 degrees Celsius, a range so cold that most materials we encounter in daily life would shatter like glass at those temperatures. At those temperatures, objects do not glow in visible light. They emit faint thermal radiation at mid-infrared wavelengths. Webb's MIRI instrument is cooled to 6.4 Kelvin, colder than the objects it is observing, which gives it the sensitivity to detect that thermal signature at distances that completely defeated every previous instrument. Spitzer, NASA's previous infrared space telescope, operated at a similar wavelength range but at lower sensitivity and far smaller mirror area. It could not do what Webb just did. The second factor is collecting area. Webb's primary mirror spans 6.5 meters in diameter, roughly 21 feet. That is approximately 6 times the light collecting area of Hubble and more than 6 times the area of Spitzer's mirror. More area means more photons captured per unit of time, which means fainter objects become detectable at a given exposure length. The third factor is the observation strategy itself. The team used what is called parallax motion stacking, observing the same field at multiple epochs separated by weeks, then computationally stacking the frames and searching for sources that shifted position between observations. Objects at Oort Cloud distances move against the stellar background at a specific, predictable angular velocity determined by their orbital parameters. The 11 sources the team found moved at precisely the rates expected for objects at those distances. That is not coincidence. That is a measurement. Now here is the part of this story that moves from astronomy into something more immediate. For decades, the standard model of long-period comet impacts on Earth has rested on a fundamental limitation. We can only measure the comets that arrive. Long-period comets, those with orbital periods exceeding 200 years, are some of the most dangerous objects in the solar system. They are large. They travel fast. They often approach from unexpected directions, not confined to the ecliptic plane like asteroids. And because of their enormous orbital periods, we typically do not detect them until they are already well inside Jupiter's orbit, giving Earth somewhere between several months and a few years of warning. For context, the Chicxulub impactor that ended the reign of non-avian dinosaurs 66 million years ago was likely between 10 and 80 kilometers in diameter. The smallest object in the Webb detection set was 11 kilometers. Not similar in trajectory, not on a collision course with anything, but similar in scale. That similarity is the point. NASA's Planetary Defense Coordination Office has published extensive analyses of the long-period comet impact threat, and every one of those analyses carries the same asterisk, the flux estimates, meaning how often a long-period comet of a given size can be expected to hit Earth, are derived entirely from comets that have already arrived in the inner solar system and been detected. It is like estimating the total population of a city by counting only the people who happen to walk past a single street corner. The people who never walk past that corner do not factor into your count. The Oort Cloud is the part of the city you have never been able to see. Until now, if follow-up surveys confirm that the density of objects detected by Webb is representative of the inner Oort Cloud as a whole, then for the first time, scientists will be able to derive the total population empirically rather than theoretically. That total population figure goes directly into the long-period comet flux models. If the real population is significantly larger than current estimates, or distributed differently, with a higher proportion of large objects, the impact risk picture changes. The direction of that change is what the planetary defense community is now focused on determining. It is important to be precise about this. We do not know yet whether the Webb detections will revise impact risk estimates upward or downward, or by how much. The 11 objects are a sample from one field of sky, observed with one instrument configuration over 6 weeks. Extrapolating a total population from 11 detections requires an enormous number of assumptions about the uniformity of the distribution, the observational completeness of the survey, and the size-frequency relationship of the actual population. The researchers know this. They publish their uncertainties alongside their findings. This is how science works. But the fact that we can now start making those measurements, rather than modeling around the absence of them, is genuinely new. The difference between a civilization-ending impact and a near miss is not inevitability, it is trajectory. And trajectory requires knowing where the objects are. So what are scientists watching now, and what would have to happen for the risk picture to change in ways that actually matter? The most immediate follow-up program is simple in concept. Recover the 11 original detections. If astronomers can reacquire the same 11 objects in subsequent Webb observations and track their motion well enough to determine refined orbital solutions, the detections move from candidate to confirmed. Orbital solutions allow scientists to project trajectories backward and forward in time to determine whether an object is on a stable, long-period orbit, whether it has ever made a close approach to the inner solar system, and whether it is being perturbed by any known gravitational influence. The second track is the Rubin Observatory, also known as the Vera C. Rubin Observatory, or the Legacy Survey of Space and Time. Located in Chile and entering full science operations in 2025 and 2026. Rubin will survey the entire visible southern sky every 3 nights, reaching deeper than any previous wide-field optical survey. It will not reach Oort Cloud distances. Its wavelength sensitivity and mirror size are optimized for the inner and middle solar system, but it will begin detecting incoming long-period comets much earlier in their inbound trajectories than current surveys can. Combined with the Webb detections, which define the source population, Rubin data will begin to constrain the rate at which Oort Cloud objects are being perturbed into Earth, crossing trajectories. The third track is the one that planetary defense planners are most interested in. NASA is developing what is internally called a next-generation comet survey program, designed specifically to push long-period comet detection times from months to years or decades. The core of the problem is that long-period comets are dark and inactive when they are far from the sun. They only develop their visible coma, the cloud of sublimating gas and dust that makes them bright in optical telescopes inside roughly 3 to 5 astronomical units, which is already inside Jupiter's orbit. By that point, we have limited warning time for anything on a collision trajectory. Webb has demonstrated that cold, inactive objects at Oort Cloud distances can be detected. A systematic survey program using Webb's capabilities, rather than a single-pointed observation, would transform the warning timeline. Keep an eye on the publication of Rubin Observatory's first-year survey statistics in late 2026. The rate at which previously unknown long-period comets are detected in that dataset will be the first major real-world test of whether current flux estimates are accurate. There is one additional scenario worth understanding, not because it is imminent, but because the Oort Cloud detection now makes it calculable for the first time. Astronomers have studied what happens when a star passes close to the solar system, close enough to gravitationally disturb the Oort Cloud. The star Gliese 710, a small red dwarf currently about 64 light-years away, is on a trajectory that will bring it within approximately 13,000 astronomical units of the Sun in approximately 1.3 million years. 13,000 astronomical units is inside the outer Oort Cloud. The gravitational perturbation this passage will cause is predictable in its direction, if not in its precise magnitude. The result would likely be an increase in the number of long-period comets displaced from stable orbits into inbound trajectories, what some researchers have called a comet shower. Evidence for past comet showers exists in the geological record, correlated with periods of elevated impact rates. This is not a near-term threat, but it is real. It is now more precisely calculable given the Oort Cloud population data Webb is beginning to provide, and it underscores exactly why what Webb just detected matters beyond the headline. Let us be clear about what this detection does and does not mean. James Webb has not found an incoming threat. The 11 objects identified in this initial survey sit at distances between 1,800 and 4,000 astronomical units. At the orbital velocities typical of Oort Cloud objects, even a body already on an inbound trajectory would require tens of thousands of years to reach the inner solar system. There is no asteroid being tracked tonight with Earth's name on it. There is no comet being watched with heightened concern based on these findings. Scientists are not alarmed. They are excited. There is a significant difference. What has changed is the baseline. For 74 years, every model of long-period comet impact frequency, every risk assessment, every planetary defense simulation was built on the assumption that the Oort Cloud exists, is large, and contains many objects, none of which we could see. We were navigating using a map drawn entirely from inference. Webb has now started sketching in the actual coastline. The researchers who published this work are not losing sleep over impending catastrophe. They are working 70-hour weeks because they know, for the first time in the history of this field, that the measurements they make right now will constrain models that planetary defense scientists will use for decades. The data is real. The population is real. And for the first time, we can see it. Go back to that question I asked you to answer in the comments. Have you ever stood outside on a clear night and tried to imagine how far space actually goes? That question has a slightly more tangible answer today than it did when you woke up this morning. We know what some of the things out at that edge look like. We know their sizes. We are starting to know their locations. If this video helped you understand something you did not before, please leave a thumbs up. Let us push for 5,000 on this one. If you want to be here for the next significant discovery, subscribe. It is free, it takes 2 seconds, and you will not miss anything important. See you in the next one.